Dear viewers, this is Deep. Today I'm going to talk about gradient, divergence and curl. It's been a while since my last video. I have been planning to make this one since then. That is why instead of making a single standalone video, I'm gonna make a series of multiple videos this time on the topic. Broadly speaking, in this series, I'm gonna explain the general behavior of a scalar and a vector field in terms of their derivatives. On gradient, divergence and curl, there are plenty of videos on the internet. However, I strongly believe that there is a disconnect between the mathematical rigor and the geometric intuition in those videos. They are either mathematically non-rigorous or too vague in explaining geometric and physical interpretation. My goal is to fill that gap in my video lectures. Let's get a sneak peek of the series. There will be 6 core videos alongside of a bonus one in this gradient, divergence and curl series. The first one, meaning the one currently you are watching, gives a briefing on the gradient, divergence and curl with some useful pointers. The second one dives deep into the derivative of a scalar field, aka the gradient. You get to see some applications as well. In the third lecture, we are going to talk about the flux integral and the net outward flow of a vector field from a given volume. The fourth one will be on the divergence. We will explore its geometric interpretation and connect it with its mathematical formula. We will get to see some applications as well. In my fifth lecture, I'll talk about the line integral, specifically the work integral. We will define the total circulation of a vector field along the edge of an area. In the sixth lecture, I will get to talk about the curl of a vector field along its geometric interpretation. We will make the connection of the meaning of curl with its mathematical expression. Finally, when we are done with the core lectures, I'm gonna present you one of the most beautiful theorems in mathematical physics, known as the Helmholtz theorem. The Helmholtz theorem ensures that any vector field can be uniquely reconstructed out of its divergence and curl only. This is why Maxwell's equations are written in terms of divergence and curl of the electromagnetic field vectors only. Let me give you a brief preview of gradient, divergence and curl. Let's start our discussion by talking about gradient of a vector field. The gradient is written as the nabla with an arrowhead, and gradient is defined as the rate of change of a scalar field with respect to position. Consider a scalar field f of r, then nabla or the gradient measures how fast that scalar field f changes in an arbitrary direction u hat. The definition goes this way. The gradient takes a scalar field f and the unit vector u hat as an input, and then in the output it gives you u hat dot grad f, which is rate of change of f along u hat. So that is how gradient is defined to be rate of change of f along u hat. Now u hat is an arbitrary direction, therefore gradient of f itself tells about the rate of change of f in any arbitrarily specified direction. Now let's talk about the divergence. Divergence is written as nabla with an arrowhead with a dot in front of it. And the divergence is defined as the total outward flux of a vector field per unit volume. Consider a vector field F and an enclosed volume V. Then divergence measures the rate of outward flow of that vector field F through that volume boundary of V from a specific point. So geometrically consider this diagram, that blue line, it denotes the volume V, and that volume V has a boundary del V. Now, with those yellow arrow, we denote those vector field F. Consider a patch ds vector on the boundary of V. So ds is an infinitesimal area. If you take dot product between F, the vector field, and the ds, it gives you the flux through ds, flux of the vector field F through ds. Now, if you integrate that F dot ds over the boundary del V, that thing is basically net outward flow of the vector field F along the boundary of V. Now, if you divide that quantity by the volume V itself, that gives you the net outward flux of F through del V per unit volume. Now, as we take the volume tends to 0, that gives us the divergence. Therefore, our divergence is nothing but net outward flux of F through del V per unit volume. Now let's talk about the curl. Curl is written as, once again, nabla with an arrowhead with a cross in front of it. And the curl is defined as the circulation of a vector field per unit area, meaning how much a vector field rotates along a point. That's what it measures. Consider a vector field F and an area that is A, which has a direction n hat and a magnitude just A. Now let's define circulation. Circulation is just work done over a closed loop. And curl measures the rate of rotation of a vector field at a specific point, basically. So geometrically speaking, consider that blue line, that is the boundary of an area, and that area is our A. And that blue line, which is the boundary of area, is denoted as del A. And consider that area has a direction n hat. Now consider a small line element dl along the edge. So F dot dl is basically a work done like quantity done by F along dl. And if we take the closed loop integration, meaning an integration over the boundary of A, that gives us the total circulation of F along the edge. Now we divide by the area A, and that is basically net circulation of F along del A and per unit area. Now if we take the limit A tends to 0, that gives us the curl of F along n hat. So basically that is n hat dot curl of F. Therefore n hat dot curl of F is nothing but net circulation of F along del A divided by infinitesimally small area A. So therefore curl of F in general measures how much a vector field rotates along an arbitrary area. That is our curl. Now we have understood gradient, divergence, and curl, all of them. Let's talk about few remarks. So first remark is like definition of gradient, divergence, and curl. They are fully geometric quantities and they are coordinate independent, meaning you can pick any coordinate, and if you perform those operations in those coordinates, they are totally independent of the coordinate values themselves. So it doesn't matter which coordinate you pick, they will always return you the same geometric quantity. Now gradient is the only first order derivative needed for a scalar field. So for a scalar field you only need gradient, and every information of scalar field is inside of that. But for vector field, divergence and curl are needed, and those two derivatives are only derivatives that are needed for a vector field, meaning you can reconstruct a vector field out of divergence and curl only, and that is given by the Helmholtz theorem. And remember, del dot and del cross, those are just notation. Therefore divergence of F is not a dot product between del and F. Similarly, curl of F is not a cross product between del and F. And do not forget to subscribe, share your thoughts in the comments. Goodbye.